Okay, in this video, we're going to talk about what happens when got both a categorical and a numerical variable about each case in some data set. That's exactly the situation we have in this table right here. This is a data set on about 5,100 students. In fact, they're all students who entered the University of Texas in the fall of 2000 and then went on to graduate within the next 6 years with their bachelor's degree. And we've got several pieces of information about them. First of all, which undergraduate college did they graduate from? And here are the 10 undergraduate colleges at UT. And then their SAT math and verbal scores. And what we've done here is take the average SAT math and the average SAT verbal score for all of the students in each of these 10 undergraduate colleges. And this is highlighting some interesting facts about variations between the groups. Probably it's most obvious in the math skills column. That's going to be more important for engineering and natural sciences majors than it's going to be for social work or liberal arts or communications. And you can see interesting stories come out here. However, I want to point out that a table like this differs from the contingency tables that we have previously seen in a crucial respect, in the sense that it collapses data. So we're not getting something about each and every person in the sample. All we're getting are these 20 numbers right here, which are telling us an average. We're not getting any sense of the variation between the cases. And so this number right here could obscure a very, very wide distribution of SAT scores. And that's where box plots are useful, and probably better than a table of sample means like this. They allow you to assess variability both between and within the groups. So let's take a look at this set of box plots right here. This is now, again, though, it's the same data set, the same 10 undergraduate colleges, and here's SAT math scores. And this picture here is giving you both the between group variation, what's the difference between a typical member of architecture, typical member of business or communications or education, and so forth. But it's also giving you a much clearer picture of the within group variation. Let's just take the architecture school as an example. There's a lot of dispersion even about this high center right here. So you may have seen a box plot before, but just to give you a sense, the black bars within each box are representing the median of that subset, so the architecture students here. And the box itself goes out to the 25th on the bottom and the 75th percentiles. And so that's a 50% coverage interval right there. And then these boxes and whiskers go up, well, there's not really any standard height that they go up to. The default in a lot of software packages is for these whiskers right here to go out to 1.5 times whatever that range is right there. And that's exactly what the default is right here. And anything outside it is shown as a dot. And so the box plot is great, showing you both between and within group variation. Here's another set of box plots that are showing SAT verbal scores by college. And just eyeballing this, if you had to say whether between group variation or within group variation was bigger, you would probably say that within group variation is bigger. So let's just take the deviation between typical colleges here is probably on the order of 40 or 50 points. The differences between the average members of an individual college. That's the differences between the black bars right here. Whereas the typical range for students within a college is something like on the order of 100 points. So here, visually, it's quite clear that the variation within a group is dominating the variation between the groups. And that it's telling you that table of sample means that we saw up above is actually a bit misleading in reducing every member of a college to some typical member who scored exactly the sample mean. Here's another example of box plot, and the situation is different here. So this is a box plot corresponding to a data set of guinea pigs. Here they are, a guinea pig in a little red wagon. What we've got here is two pieces of information. First of all, what dosage of vitamin C was the guinea pig given? Guinea pigs actually have to be given vitamin C. They can't synthesize it themselves, just like us. And there's 3 levels here of the dosage factor. There's 0.5 milligram, 1 milligram, and 2 milligrams. There's your categorical variable right there. And then there's a numerical variable, tooth length, and that's sort of a proxy for the overall health of the little guinea pig. And what you're seeing here is that now there's much more between group variation. The vitamin C is a huge predictor of their tooth length. There is still within group variation, but now think about the differences between, say, that bar and that bar is very large. on the order of 10 or 15 points, whereas the variation within a group is on the order more of like 5 or 6 points right here for tooth length. And so here's a case where within group variation is smaller than between group variation. And the box plot is giving you both. That's why it's such a valuable tool for visualizing numerical and categorical predictors together. Another way to do this is by a dot plot, and this is sort of a drop-in replacement for the box plot. It is literally every single dot represents a case. Okay, so this is a different data set here. What you're looking at is a whole bunch of dreaming animals. Okay, so the y-axis here is the number of hours that animal dreams per night, as measured presumably in some little fMRI machine appropriate for a possum or a skunk or something. Every dot is an animal, and the animals are grouped into this ordinal variable right here called the predation index. I don't exactly know how this is done. It's something that the ecologists come up with, but the idea is 1 to 5, and that's in increasing danger of predation, which probably has to do with whether it's a prey animal to begin with, what kinds of predators are out there, waiting to snap it up. So 5 is most in danger of predation, 1 is least in danger of predation, and the dot plot is showing us a very clear story. The blue dots here are like the sample means of each of these groups, that the more danger you are in predation, the less you dream, probably the less soundly you sleep altogether. So the dot plot is really nice if you've got a pretty small data set. You can show the individual points as opposed to reducing them to the box and whisker plot in the box plot. One thing you may notice here is that there's some differences on the horizontal axis here. That's totally artificial. That's just a little bit of jitter that's been added to these points so that you can distinguish them individually and they don't all line up on a vertical row. Dot plots also work just fine for big data sets too. Here's an example of daily peak electricity demand stratified by month for the city of Raleigh, North Carolina over a period of about 4 years. Here's the month of year as your categorical variable and daily peak demand in megawatts as your numerical variable. And there's a very clear pattern. I'm just kind of connecting the dots among the sample means so you can see the cyclical pattern as we go from warm summer months to cold winter months over here for electricity consumption. But the dot plot is showing you that there's a whole bunch of variation even within an individual month that probably swamps the between group, the between month variation, the differences between the blue dots right here. Now, these blue dots right here, we would call those the group means, and this sort of gives us a useful decomposition of an individual case, and I'll refer to this many times throughout the course. What we're doing in a dot plot is really about the simplest statistical model that we can fit. A statistical model is going to partition the individual observations into a predictable component and an unpredictable component. In the case of a dot plot, the predictable component is just the group mean, right? Like for March, for example, that would be your best guess using only month of year as a predictor. And then there are a lot of errors or residuals associated with your best guess. And so we're decomposing the individual case into the group mean plus the deviation or residual associated with that case. And another way to write that is in terms of the grand mean, which is the overall mean. Going back to the plot, that's like this dotted horizontal line right here. That's the grand mean irrespective of month. And then you could also think about each individual case as the grand mean plus the deviation of its group plus the deviation of the individual case, and that's what that simple little equation is saying right here.